direction?
No. You can start showing the telescope. Anyway, you are here.
You are starting it now. Okay, but we can. If the camera shifts somewhere,
Yeah. So
you
you are saying?
you can have a conversation. You can stop it.
Okay. Then yeah. Okay. Start.
Satya.
Online. Yeah. Good evening, everyone. So today I'm standing on the Vinupapu observing floor. As you can see that this telescope is dedicated to Vainu Professor Vainu, who was the founder, director of Indian Institute of Astrophysics. This telescope was dedicated to the nation on January 6, 1986 by our Prime Minister, then Prime Minister Rajiv Gandhi. This is the telescope structure. As you can see that this telescope is basically on two pillars, which is completely isolated from the entire telescope structure. Basically, not to put any vibration onto the telescope while the dome structure is moving. This telescope is 2.34 meter, and when you say 2.34 meter, this is basically the diameter of the primary mirror, which is at the base of the telescope structure. And this telescope moves on two axes, but one of the axes is basically fixed, and it points towards the North Pole. Now I'll show you some of the movement of the telescope. So you will now see the movement of the telescope. Now it is looking towards slightly towards the North Pole. Now we will move it and make it to the zenith. So you will see that this movement which we are showing now is basically to the declination direction. So any star on the sky is identified basically by two coordinates. One is the right ascension and another is the declination. So right now you can see that the telescope is moving towards what you call zenith, which is a point, a fictitious point right above our head. So you can see the telescope is moving in the declination direction. So if you want to point to any stellar source or celestial object for that matter, then we need to know what is its coordinates, basically in right ascension and declination. So now once you give that coordinate into the console, then telescope moves to that particular location. So now it is moving towards the zenith in the direction of the declination. Now I'll show you how the telescope moves in the right ascension. Basically it now comes towards east or towards the west direction. So you can move it to east. So now you will see that the telescope is will move towards the east direction, and the movement is made possible by the horseshoe structure that is towards one of the direction, and this is one of the largest horseshoe structure made in the country. Let me also tell you that the entire structure, the telescope structure, is made indigenously in India by the Indian industries, and the housing and the dome was made by Tata consultancy engineers. So right now the telescope is moving towards the east direction, where you can see that it is moving very smoothly. This is the movement of the telescope has to be so precise because the stars that you see are in arc of a second. Now you can see that at the top structure. At the top structure, you can see the primary mirror. So the light from any celestial source will come from the top. It falls onto the primary mirror, goes back, reflects from the secondary, which you can see there. It's called the prime cage, and the light comes back and goes to the Cassegrain Hole. Now I'll show you the operation of the dome, where we will dome what is called the dome slit. So the telescope has to point to a celestial source, and the dome slit also has to move towards there so that we can observe the source. The dome is required basically to cut any unwanted light that is coming from other regions, so that we can point the telescope only towards the region where we are interested. So now you will see the dome slit opening. So now you can see that the dome slit is opening, and you can see the blue sky in the background. If you can appreciate that, if you can see whether the telescope is moving, looking through the slit or not. So right now it is not looking through the slit. So what we can do is we can move the dome. We can move the dome towards where the telescope is pointing. So now you can see that the entire dome of the building is basically rotating, so that the slit opening can be aligned with the telescope. And during the observation, the dome and the telescope is synchronized, so the movement is linked. So whenever telescope moves, and if the opening of the slit is not aligned with the telescope, it automatically moves and aligned with it. So now you can see that. So now you can see how the telescope and the dome is the telescope and the dome slit is getting aligned. And now we can see how the light that is collected by the telescope is gathered, and then we pass it through the instruments that are attached to the telescope, and we can either do an imaging of the sky, or you can do spectroscopy of the sky, of the star. So imaging is basically done either by putting a CCD or attaching a CCD to the primary focus, or this can be done by by attaching the instrument to the secondary so now the telescope is going back to the zenith, where the telescope will be looking towards our overhead. Now we will see what is called Cassegrain Hole. This is the region from where we get the light from the light from the celestial source comes onto the primary. It gets reflected back reflected back and reflects through the secondary mirror and comes to this Cassegrain Hole. And here is where we attach the instruments to gather the light to basically do imaging or spectroscopy. Right now, here we have two instruments. One is the spectrograph, and another is a high resolution spectrograph, which is called the Echelle spectrograph. And the light is collected from the star by putting a fiber onto the prime focus, and that light is taken and then fed through a spectrograph to get very high spectral resolution of the sources, basically to study the chemical evolution of the sources of the celestial objects. So yeah. Any questions regarding what is explained now can be asked. Oh, it's it's okay. If there are any questions, you can post it on the email, on the YouTube chat box. We can answer. So the telescope. Okay, so now we will take some questions. I'm joined by the Director of Indian Institute of Astrophysics, Prof. Annapurni.
Hello, everyone. Yeah.
So the question is from Kiran Murthy, who says, can we see the output by the instruments?
Yeah, that's an interesting question. So Mahesh explained that the where you connect the instruments, which collects the telescope collects the light, and the instrument records it, either in terms of by means of an image or a spectra. So now the question is, can you see the output which is captured by this instrument? Of course, yes. So what we do is we have a place where the computer actually captures it. It's a digital image, and you can actually process it. I mean, you can actually display it after the integration. Like the camera integrates it for about 5 minutes, 10 minutes, 15 minutes. After the integration is over, it reads out and it is displayed. So as soon as the observation is over, we have a provision to display what is captured by the instrument, and maybe some preliminary analysis. But later on, this digital image is used for further scientific analysis. Hope I answered that question.
Yeah, the next question is also related. How does the Vinupapu telescope does the imaging? I think
so that the answer is that the light is collected in the primary mirror. It goes up to the secondary mirror. It gets reflected back. Behind the primary mirror, we connect the camera. The camera is something very similar to the camera you have in your mobile phones. So that picture is an image, and that image is used for scientific purposes. But of course, it is not like a general camera. This is a scientific camera along with wavelength identification, etc.
Yeah, the next one is a general question that people often ask. What is the size of the lens of this telescope?
Yeah, so can you imagine making a lens with the aperture is about 2.5 meters? The lens, this much of thickness of the glass, and done like this, it's so heavy. So once the size of the telescope becomes bigger, we do not have a refractive system, but a reflective system. So instead of a lens, these telescopes have mirrors. So bigger telescopes always have mirrors and not lenses. But smaller telescopes, lenses can be used.
Yeah, I think the mirrors are easy to support also.
Yeah, and fabricate, and the weight is less. Correct. Now you use a lightweight mirrors, so overall mechanical weight is also reduced. And so we have the mirror technology to make mirrors, but we can make up to 8 to 10 meter. Beyond that, we can't do that, yes.
And nowadays, we have segmented mirrors.
Yes, yeah. That is how you have the Keck telescope, etc.
Yeah, and even the JWST, which is...
Yeah, so that is the first segmented up in the space, yeah. That's nice.
So the next one is, what is the biggest achievement of this telescope from the establishment to present?
Yeah, so that's a very interesting question. Initially, we had used this telescope to look at globular clusters. The images were excellent. But then at the time when it was established, this was state-of-the-art telescope. And that had several good images, galaxy images, studies of star-forming regions in galaxies, studies of supernovae, novae, and elemental abundances. Actually, this is one of the telescope which has got high-resolution spectrograph. What it means is the light collected can be chopped into various wavelengths. And this wavelength actually conveys, like if you have some particular lambda or some photon missing, that means that photon has been absorbed by the molecule or the ion sitting on the star. Correct. Right? Yeah. So if the presence of that particular absence of your light tells you that someone ate up that light, correct, and that happens to be an ion in the star. So that, if you can say which ion it was, it reflects, tells you exactly what is the abundance or fraction of that particular element present there. So this telescope has contributed to identifying elements in stars. Stars of various types of different elements. So this is a major contribution because of the spectrograph, high resolution spectrograph. So elements like lithium, elements like fluorine, and many carbon, nitrogen, oxygen of nebulae, stars, etc. This telescope has contributed. So that is the most important thing, the high resolution spectrograph.
Yeah, the next question is also interesting. This is what many people ask. Is there any new star discovered using this telescope?
Yeah, so new star, how do you define a new star? New star can be a star which is born, which is new, or a nova or a supernova. It's a new star. But it is not a new star, it is like a faint star. It became new because it became bright. So supernova is also like a new star. So we do study, like you study star formation. So star formation sites, that the birth sites of star formation. So in general, over the years, almost all the stars are catalogued. But the fainter you go, you may find new stars, not the bright ones. But very faint ones, depending upon the depth of your observation, you might find fainter brown dwarf, or closer to the end limit of the stars, right? That happens.
Right.
So you discover brown dwarf or less massive stars in a cluster because you are going deeper.
Right.
Yeah, okay, so that's a nice question. Yeah.
Yeah, so the young stars, you can say these are like baby stars which are recently been born. So you can study about them using the instruments that are attached to this telescope. Okay, the next one is, which telescope is best land telescope or Earth orbiting telescope?
Okay, so let me rephrase this question. So this thing is, which one is the best, one on the ground or the one in space, right? Okay, that's a very, very interesting question. How do you define the best? That is very qualitative. So you can define the best by the sharpness of the image, how much deeper you can go, or which wavelength you can see. So it is, nowadays, people are not chasing the best, but best across the wavelength. So to study an object. So what happens is, you may get an optical light from a telescope, very good telescope, but that data itself may not be able to tell you all the scientific aspects of that object. So you combine all the wavelength. So partly you get it from the ground. You can't have too many, because ground telescopes are still cheaper than sending telescopes up in space as well as operating. But you cannot, certain wavelengths you will not get on the surface of the Earth. For them, you have to send them in space. Like India's first space observatory, AstroSat for that matter, X-rays and UV. So you have to send them up. But these days, multi-wavelength observations and simultaneous observations do give a lot more scientific insight into the science behind these objects. So the best happens to be a combination of telescopes, not just one telescope.
So I think we can take one more question. Curious to know, like, how far we can use the telescope to study the Surya. Basically asking how telescopes can be used to study the sun.
Yeah, the sun, the Parker probe went closer to the sun. So sun has, sun is the closest star, and it has a lot of light, so you can have resolutions as much as possible, but it's very dynamic as well. So you have to keep synoptic observations as well as continuous observations and the long-term observations to study. And also, like, it has got inner photosphere, then you have a chromosphere, and then the corona, and the magnetic fields, and the interplanetary things. So it becomes, it's not, are you looking at closer, or are you looking at entire range? So it depends on what science you want to do with the sun.
Also, you cannot study the sun with
this telescope.
You need to have a special kind of telescope.
Yeah.
So I think, thank you very much, Professor Annapurni, for answering the questions.
Thank you.
Yeah, it's really a pleasure.
So we will wait for a few minutes and then start the next program, right? Yeah, please hold on.
Yeah.
We'll be back with more interesting things.
Venkatesh. நானே பண்ணிட்டு விசால் போடுறேன். வெங்கடேஷ்
them to bear with us and then move on with the program. So please, I am really grateful to you, sir. Good evening, everyone. And I'm really happy and it's a pleasure for us and grateful to have two dignitaries over here. Shri Somnath, he's the current chairman ISRO, and Dr. Radhakrishnan, he's the ex-chairman ISRO. And I think it's really, we are really lucky to have them here as part of the National Science Day celebrations. And I welcome them to the floor. And this is the historic Vinupapu telescope building. And we honor our guests now, Shri Radhakrishnan. Shri Somnath. Just a brief few words of introduction to our guests. They do not need any introduction, but just to fill that slot of introduction as a formal part. Dr. Radhakrishnan headed the Indian Space Research Organization between 2019 and 2014. And prior to this, he was the director of Vikram Sarabhai Space Center and then the director of National Remote Sensing Agency of the Department of Space. He also was with the Ministry of Earth Sciences as the director of Indian National Center for Ocean Information Science Services, INCOIS. She graduated in electrical engineering from Kerala University, completed also the PGDM at the Indian Institute of Management, Bangalore, and then doctorate with his thesis titled Some Strategies for the Indian Earth Observation System from the Indian Institute of Technology, Kharagpur. He is a fellow of the Indian National Academy of Science, a fellow of Indian National Academy of Engineering, and honorary life fellow of the Institution of Engineers, India, honorary fellow of the Institution of Electrical and Telecommunication Engineers, India, and member of International Academy of Astronautics. He has been awarded the Padma Bhushan in 2014 by the Government of India for his contribution to science and engineering, especially in the field of space sciences and technology. He is currently with the Indian Institute of Technology, Kanpur, and also heading several other positions as members and heading several committees. So really, we are grateful to him to visit our observatory and be on the floor of the Vinupapu telescope. Thank you so much, sir. And Shri Somnath is the secretary to the Department of Space and Chairman, Space Commission. And his previous assignments, he served as the director of Vikram Sarabhai Space Center, Director of Liquid Propulsion Systems Center, LPSC, Associate Director Projects of Vikram Sarabhai Space Center, and also the Project Director of GSLV Mark III launch vehicle. He's an expert in the area of system engineering of launch vehicles. His contributions in PSLV and GSLV Mark III were in their overall architecture, propulsion stages, design, structural and structural dynamics designs, separation systems, vehicle integration, and integration procedure developments. He's a fellow of the Indian National Academy of Engineering, fellow of the Aeronautical Society of India, Astronautical Society of India, and a member of International Academy of Astronautics. He has published several papers in journals and seminars in the area of structural dynamics and controlled dynamic analysis of separation mechanisms, vibration and acoustic testing, launch vehicle design, and launch services management. He is widely traveled as delegate and representative of India in the UN COPUS in Vienna, International Astronautical Federations, International Program Committees, International Astronautical Congress held in different countries. He is the Vice President of the IAF in charge of the technical activities and a member of the Technical Committee for Space Transportation and International Project Program Management Committee. So we are really grateful to him, and thank you so much, sir, to be here on the National Science Day. And as part of this program, we are talking to them as well as giving them, telling us about their experience, their journey in space science and technology, and how what has been achieved and how the future looks like. So I request them to speak a few words on that. Sir, you can come here. Yes.
Thank you very much, Dr. Annapurni Subramaniam, and all colleagues of Indian Institute of Astrophysics, as well as the persons who are manning this observatory. We are also extremely happy that we could persuade Mr. Somnath to join us today. And we will have a few question-answer sessions, maybe up to 8:15, 8:30 we could go. What is common between IAEA and the space community? We are all looking at the stars, the sky, the universe. So humankind's quest to understand more and more about the universe, where we came from, and where are we going to be in the future. In a time domain that is quite large, of course, to know more about the solar system. And this part we call it the exploration. It is very exciting, whether we observe from the ground and come to conclusions, or whether we get out of the atmosphere and use satellite systems for looking at the universe. And you have been partnering with ISRO in a very major program, which is AstroSat. And one of the instruments that was jointly done by ISRO, IAEA, and the Canadian Space Agency is supposed to be one of the best in the world today in terms of its spatial resolution. And of course, the science that AstroSat has brought is something which is very commendable, and a few discoveries which are great. And if you look at a program like AstroSat, it has challenges for an engineer of various disciplines, for a scientist, and those who in these days look at data analytics, big data. So this is something which has happened, which is a very creditable achievement. And if you look at the history of space observations, the Kepler was there. Of course, the Hubble telescope was there, Herschel telescope was there. Now we have the James Webb telescope, which has enhanced the possibilities for doing more and more research. They are very complex systems, but in that family, AstroSat still holds an important niche for the global astronomy community and the Indian astronomy community. And of course, IAEA has been involved not only in building instruments, but using the data and coming to scientific conclusions about it. Recently, we also heard about the Parker Solar Probe, which has come very close to Sun, which is something like 6 million kilometers close to, after a long journey which started in 2018. And India has, in that area, an observational program which is Aditya L1. We will learn more about Aditya L1 from Dr. Somnath subsequently. And something that India tried in the year 2000 plus, which was earlier building satellites to be orbited around Earth for communications, for remote sensing, got into another realm and started looking at moon as an object where we wanted to have an orbiter to study, to image, to understand more the intricacies of getting into moon. And that was the time world had a lot of experience in this area, but for some time there was an inactivity in terms of lunar exploration. And then there came a renewed interest came. And many more players started, including Japan, China. And India stood along with them in that club. And by 2008, we had the Chandrayaan-1 mission, which was technically a very important achievement. Scientifically, another achievement where Indian-built instruments were also in that mission, which provided excellent inputs, excellent images of very high resolution, very high level of height accuracy in terms of terrain mapping. And it also provided a platform for international collaboration. And NASA, European Space Agency, and many other institutions were given an opportunity to fly their scientific instruments on board Chandrayaan-1. And of course, some of those instruments from NASA gave us new discoveries about the abundance or presence of water molecules, water ice, etc. So this was a very major milestone. And that was the time the Japanese mission had gone there, the Chinese mission had gone there. So we were contemporary in the renewed lunar exploration. And the next step of it was, of course, the Mars Orbiter mission, which we started in the year 2010, and by 2014, we could achieve. We learned from our own experiences, we learned from the experiences of the failures that the forerunners in this field had for their 50 missions. And in the first attempt, of course, we were able to orbit successfully, precisely, a satellite around Mars, with a few scientific instruments that we could manage within that small period. But what we proved at that time was India can successfully navigate a spacecraft to reach moon, which is a very complex job, and as scientists, we don't have to explain what is that complexity. Whether it is about the distance, whether it is about the long traverse involved, whether it is about the accuracies required in the trans-Mars injection or the orbit capture after a long journey of 300 days. That we achieved. The next step, of course, is to build wonderful instruments, to look at new themes that one needs to understand, what the humanity needs to understand about Mars. That is the next step. So we will hear from Dr. Somnath about what is in the anvil at the moment in terms of Martian exploration by India and collectively with the rest of the scientific community in the country and abroad. So this is another theme which has come. Aditya was a wonderful initiative. Initially it was supposed to be a satellite around Earth looking at Sun, but thanks to the guidance given by Professor U.R. Rao, the Chairman, Advisory Committee on Space Sciences, he said we should go to L1. And we also should have more instruments, not only the coronagraph. And that is what is now getting ready. And I'm sure that IAEA is playing a very important role in Aditya mission. Now, these are all about the scientific exploration that we are doing today. Of course, in the solar system, there are other planets to look at beyond Mars. There are other neighbors. Venus is another target. Like that, there are many issues to be understood, and we have to study. And if you have to make fundamental new studies in space science, the most important thing is to build scientific instruments worth doing that science. And one message is the scientific community need to envision what are those scientific objectives and what kind of instruments that we need to conceive first and build. It need not be complex, but it has to be novel, and it has to give good results, reliable information. And that is in front of us, which requires engineering, which requires understanding of science, and which requires how to analyze that data to good conclusions. So this is a challenge in front of the scientific community. These days we talk about another area, how to exploit the resources in the celestial objects like Moon, like Mars. How do we have habitat in these celestial bodies? What is involved if we have to take human being there, keep them there, and also bring something back to Earth and the people safely? And can we have robotics, space robotics, to aid the human space exploration? This is something for the future. This has complexities and challenges for the entire space community. And if you have to bring back 10 tons from Mars, The preliminary calculations are that we need to have capability to put 250, 275 tons in the low Earth orbit first. From there it goes to Mars. It orbits, it lands, it does its job there. Then we have to come towards Earth safely. There are so many complexities. I'm just putting it in a very simple way. Then why do we have space in India is a question which our founders asked and answered. That is for the people. There is a humanity and you have to help the humanity. Space applications for humanity. This is the USP of Indian space program. So that continues to be, whether it is space observations, remote sensing and use of the data about Earth to look at today's sustainable development goals or the climate change or look at agriculture, water specifically or forest, etc., etc. Or to use the satellite systems to help those who are managing the disasters, support systems. These are all areas in which India has excelled. Security is another dimension which has come in the recent years. Now, if you have to do all this, you require technology which gives us the capability to do all that we dream. And of course, there is no best person in the country who can tell you about that part of it than Dr. Somnath. And finally, when you talk about space today, the word used is space economics. And we talk about 400 billion US dollars of space economy by almost 80 nations. 70% of this economy is coming from the commercial operations. And India has today another major initiative for space sector reforms to ensure that we catch up. And where has been India in space area? About 6 or 7 in the world is India. So we need to not only retain that position, we need to also advance. So this is the challenge in front of the community who deals with outer space activities in the country. And certainly, as I said, it is challenging, exciting, and the world is changing very fast. And in space, the lead time for any major mission could be 10 to 15 years. AstroSat was thought about in the mid-90s, and we got it in 2015. So you look at, but of course we did a wonderful job there. So we need to think in advance what needs to be done. And aside the technology is advancing, which is helping us to do many, many more things which are not possible. So these are all the possibilities in front of us. And I stop at this moment of time. I will ask Dr. Annapurni to say a few things and ask questions, and I will request Dr. Somnath to address some of the questions. And I also should tell you that he is my teacher on technology. Thank you.
Yeah, so thank you so much for setting the stage as well as, giving a broad overview of technology and the missions and science and how does one connect science and technology and how do one visualizes, to move forward. So that is a very interesting, nice perspective, including space, economics, and everything, technology and everything together. Thank you so much, sir. So maybe we would request Shri Somnath to say a few words and then we can take questions.
Thank you, Dr. Radhakrishnan, for setting the stage for today's program. And also thank you so much for being the partner with ISRO for very important missions that already Sir has mentioned. And some of the wonderful science that you could do with those instruments. Now it takes me back to the theme of today's program, that is the National Science Day, which is celebrated only on 28th of February every year, marking the C.V. Raman effect finding. And it's very appropriate that you organize this program. Primarily, I believe it is not only to enthuse the scientists here, but also the young people across the country who is actually aspiring to become astrophysicist. Wherever a young boy or a girl comes to us and they talk about science and space science, everybody says, I want to become an astrophysicist, not a rocket scientist. I always envy. Why they are so telling like that, not becoming a rocket scientist like me? But doesn't matter. It is their dream to become an astrophysicist. I believe that your work in IAEA will really inspire people across the country to become astrophysicists. In that path, they may become some rocket scientists as well. So let it be so. So let me tell you that the humanities' knowledge about the universe, how it evolved around us, how it is determining us future, everything came out of observations. Right from the days when we had bare eyesight observations to the telescopes. Today, you know that the space technology enables us to sit somewhere out above the atmosphere of Earth and then in the space and look far beyond. Now, this capability came to us only because that we had the technology called rocket science. The ability to overcome the gravity field of Earth and move a mass to the orbit and then keep it there for years together. That enabled us to look at deep into the universe and then understand the universe. I think this is really wonderful capability that humanity now have. And the type of instruments that we placed in orbit, like the Hubble, the Kepler, or the Chandra, or even the Astrosat, gave such an insight into the evolution of the universe in the last 30, 40 years, which never ever the humanity could, gather. And I believe that the space technology has this strength to enable human beings to not only to go there and observe, now enables you to travel beyond Earth, go foot on the moon, the Mars, and sometimes the exoplanets to create the spread of the humanity all across the universe. I think this is what our desire is, our goal is. And that is what space technology is for. And today when we celebrate the National Science Day, I would like to tell you that the space technology today is one of the important tools that the nation need to have a command on the science front. In India, space technology came out because of the inspirational leadership provided by people like C.V. Raman and his children or their students like Sarabhai, created the space community in India, the space activity in India, which is now known very well as one of the leading spacefaring nation of the world, having its own capability to build instruments, the satellites, and also having rockets to launch it from its own soil. And it is not a small achievement that we have. Everything started at Tumba when we were building small rockets to go up and look at the equatorial electrojet phenomena way up in the atmosphere where they above the electromagnetic equator. And this started as a space science activity many years back. Today, it has reached the level of Astrosat. And it is now going to go further beyond in building capability to have more observations. As Dr. Radhakrishnan has already mentioned, the science part of the space science is not only limited to looking at celestial objects. It needs to look at the Earth. We look at the atmosphere, the interaction of the atmosphere and the what you call the geosphere with the and how it shapes our lives, sustainability, etc. is one of the important goals. Then we also look at the space part of it and how the space weather, for example, influences our life. And we have seen recently one of the very serious events and how we can model and predict such events in the future. We also want to understand what happens in the faraway galaxies and planets and to understand how the universe evolved. We want to understand what is there in exoplanets, whether the mineral content, the atmospheric structure, the temperature, the presence of water molecules or presence of water for human beings to migrate there and stay. All these are concerns that is now for the humanity. And we need to develop technology from today and tomorrow to enable human being to become a multi-planet species. This is something that we all look for. In the recent times, I think that discussion on this has become much bigger, much better, primarily because the bigger rockets are being developed. The cost of access to space has come down per kilogram that you put in orbit has come down drastically because of technological growth in this. And even we are envisioning that human beings will travel to Mars and make colonies of lack of people and then create a possibility for a human being to travel far beyond that. And I'm very sure all these are going to happen. It is not a pipe dream. It is something that is going to happen in tens of years from now, maybe few years from now. but definitely human beings are going to create the capability to travel far beyond the solar system. I have no doubt about it. As whatever we are doing today are the baby steps to enable us to move towards the direction. I think this is something we need to recognize and do our part of the work. In ISRO, we do space science activity quite a bit, as Sir has already mentioned, in terms of planning and executing science missions, along with the very important missions which are required for the nation, like the remote sensing missions, the communication missions. We do that, but these part of the missions, the science missions, are only a very small segment of that overall activity of ISRO. But we bank on not only ISRO scientists, but bank on the scientist pool available across the country. Iaea is very definitely one of the very important scientist pool who have the capability to build instruments and then create science out of whatever support that ISRO can provide. And this is what we really did in the AstroSat. And we wanted to replicate this in the future missions, as Aditya L1 is one of the important missions that has been conceived to look at Sun and understand its influence on the way the people live in Earth. I think that interaction is something that we need to model and understand and predict for our survival and even our system survival. Whatever we put in space is also, its life is dependent on how well we understand Sun. It is not going to stop with that. We are going to see many more instruments and missions that are yet to come up. For example, the Venus mission, which we are thinking about. I think probably some of you may be already knowing about Venus quite a bit. I am not the right person to comment on it. And I have been reading about the type of studies our scientists in ISRO has done on possible missions to Venus and look at its atmosphere and where human beings can actually go there, create colonies even in the upper atmosphere, floating there in balloons, because the pressure there is quite high. So the 1 atmospheric pressure is available something like some 80 or 90 kilometer up in the atmosphere only. So how to create a stratospheric balloon type arrangement. How to go and then even enter deep into the Venusian atmosphere through aerodynamic decelerators, go down and then take measurements at the deep acidic environment which is existing in Venus. All these discussions, in fact, I have been reading, understanding. I think IAEA can come up with maybe novel instruments and approaches to study this. I know many other scientist pool in this country are also looking at it. Such a mission has been now conceived and we are currently in discussion how to get approval from government to even take it further. I can tell you it's not going to stop there. I think our ability to put very good instruments and spacecrafts in Earth orbit and far beyond it will only enable us to look deeper and contribute our part. Our part means India's part in the knowledge of our universe, to be comparable with what others have done in this world, maybe comparable to many others in the scientist pool across the globe. I think this is the goal that we need to pursue. I want to also only offer that we will do whatever we can in ISRO to encourage you to take your goal of observing and understanding the astro part of it through our hosting those payloads in our missions. I think this is something I would like to offer. I only want to tell you, I have only very limited knowledge of the scientist pool in IAEA, I must admit. I only knew about quite a little bit about all of you. But then it is something that interaction need to increase, and like many other scientific and research establishments existing in this country, IAEA need to come forward to take up this challenge of creating very strong scientific capability in this country. In ISRO, we have many more programs. I think probably you know them. We have been offering our PSLV as an experimental platform for you to conduct experiments in space. Probably it may not come under your realm of scientific research. Maybe some other people may be offering, primarily looking at the outer atmospheric research. We are also looking at how human space flight capability that we are trying to develop through the Gaganyaan can be used for conducting experiments in space. So, for example, when we announced this Gaganyaan program, there were so many ideas that came to us in terms of taking up the microgravity experiments, even synthesis of medicines and other bio experiments that can be hosted on board of the Gaganyaan and then brought back and then tried out. Experiments on metallurgy and material formation, because very pure crystals can be formed in zero gravity environment, which will enable very good research in material science. A lot of scientists pool are very keenly looking at human spaceflight capability and presence of human being to carry out certain experiments. Probably some of the experiments that you can think can also be aligned to the capability that we are going to develop in the future. Human beings are going to be there, and Indians are going to be there in the orbit one day. So please prepare yourself to do some experiments in that direction as well. And we really are creating a type of vision for the next 20-30 years in the science domain. It starts with capability to build rockets and launch them, enhance our capability to launch much heavier payloads in the orbit. As Sir has mentioned, we need to have higher payload capability to really do experiments far away from us. We are also looking at how to create the human space capability, which increase our ability to conduct certain experiments which is not possible otherwise through robotic means. We are also trying to look at how periodically we can host scientific missions along with the national mission goals that we need to achieve. For example, Disha L, there is a satellite which we are trying to look at the as aeronomy part of it. So this is another experiment. Possibly there could be many other experiments that can come out. One of the interesting experiments is exosolar planets study, so we call exo worlds. There is a satellite which is currently being conceived to look at the atmospheric and mineral composition of exoplanets. So many such ideas are there. So I would like to take this opportunity to congratulate IAEA for their excellent work in building new instruments and also creating good scientist pool in this country, astrosat scientist pool, right, the terminology is astrosat user community in this country to take the whatever opportunity provided by ISRO to its fullest. Thank you once again. I take this opportunity to thank IAEA for this event, and I'm sure we will have closer and stronger interaction in the days to come.
Yeah, thank you so much for sharing the your current and future plans. Yeah, we have people there, and we also have very distinguished guests in the room as well. So I think we can have a few questions from people. So let me start from, yeah, so I just wanted to ask, now the...
Anticipatory bail. There are questions which we know we will answer. There are questions we know but we are not supposed to answer, that we will not answer. In science, there may not be many, but that is the situation. And there are answers which we may not know. We don't guarantee that all questions will be answered. Okay, thank you.
So general question, like, everybody is looking to space now. All the countries are, looking to advance their space technology, have a footprint in space. So have a location in space. So where are we leading to? Like, do we have any understanding of how cooperation between nations, and what is your view on this, how we should have, because, right now, I don't know whether any kind of a treaty or how much space is available kind of a thing. So what are your views on this particular?
There are two dimensions when the space program started and the modern space age began in 1957. Initially in the bipolar world, there were treaties. There are a few which talk about the do's and don'ts in Earth space, even in celestial bodies. But afterwards, things have been through guidelines, etc. So this is a regime which is evolving in the modern day, in the multipolar world, where there are more number of players. One very major platform for this is the UN Committee on Peaceful Use of Outer Space. India has been one of the founder members of UN Corpus. At that time, there were only a dozen nations who were interested in getting into that. India was one among them, and one of the first member formally. And India has been playing a very major role. And I also should say, in that body, on space applications, India has a respectable lead role. I also have been sitting there for some time, and we could see how other nations take India's experience, not only in making something possible through space data, but scaling it up for a nation which is very complex, for different types of problems, and making it part of their value chain. And that starts with our initial vision that it should be useful for the people of the country. Okay, that is number one. The number two, when you look at entire outer space, we are a minuscule element in this universe. And when we are looking at interplanetary missions, interplanetary travel, exploitation, etc., why should a very small nation repeat the same thing? And this is a costly affair, it takes time. So what is happening today is bilateral and multilateral cooperation, collaboration in this area. First, competition will be there. That only enhances one's capabilities. But this is something which has happened. From that competition of the 50s, today it is cooperation and collaboration. So you have large projects. There was one initiative a few years back whether they talk about global exploration strategy. A few countries sat together and said, how can we look at Moon and Mars in a different way together? More and more some such things will happen. Regional cooperation is another thing, when it specifically going to applications. When you talk about disaster management today, there is a program called Sentinel Asia. Several nations in this area, they contribute. When something happens in one part, all other countries come together and provide satellite data, timely data, etc., etc. So these things are evolving. There is also regional commerce in communication, especially. If you look at Intelsat, Arabsat, etc., these are all such consortia. So this is another aspect. Now the major question remains when you look at celestial bodies, what about the ownership, what about the do's and don'ts, etc., etc. This is the challenge in front of the new generation. How do we write that, and how do we put our footprint there? If you have to have that footprint there, you must do something first. Then you have a voice in deciding about the future. So how they will do it, he will.
No, this space area is an area where there is both competition and cooperation. It simultaneously exists. Competition in terms of the high-end technology that you have at a given point of time is not available for sharing. But at the same time, the fruits of space technology can be shared. So for example, I can tell you, there were examples of some of the cooperation that happens currently is International Space Station. International Space Station is an example of how different nations, even the earlier Cold War enemies, can come together to run a space station. No, it is an example of that. Now we have similar examples other places also. Even now, new examples are emerging. Currently, the Artemis program, which US is proposing, it's a moon program where multiple nations can join together to create a space station around moon. Sarah has mentioned about the application side of cooperation. There are forums where we do this. In India, we have a similar cooperation agreement with maybe almost 100 nations. We have signed MOUs of agreement of sharing and working together with different nations. Some of them may be in a very low level, some are very active. We have hosted payloads from NASA in our spacecraft. We are working out a Indian-American joint satellite called NISR, which is going to be launched soon, which is a very synthetic aperture radar satellite operating in 2 bands, simultaneously, primarily looking at agriculture usage. So this is one common platform where investment is from NASA and investment from India, and we want to build a satellite which will be useful for both the countries. So similarly, we have done projects with France. At least 2 satellites we have launched, and it is one of the best satellites that helped to understand the ocean, atmosphere, as well as agriculture domains. So, and we are going to work with Japan in the coming days to look at how we can go and land in moon together using the technologies available in these countries. So definitely there are cooperative movements, but at the same time you should also realize this is a national strength and you don't want to give it away to anybody. So you work to keep certain technologies with you, but we also look at how to cooperate to generate a common goal, good.
So thank you so much. Is there any question from YouTube, or shall we take questions from, I think we'll take questions from the audience. So we have a couple of distinguished audience here. So one is producer A.V. Anup, and we have Vinod Mankara, who's a famous film personality. So I take a question from you, sir, on, yeah, you can come onto the camera and then you can come over and just turn around.
Thank you, madam. Thank you, madam. I'm delighted to be here. This is the first time I'm visiting an observatory. Yes, I'm A.V. Anup. Managing Director of Iaea Group. We make Medimix soaps and Melam Masala. I'm also into Ayurvedic hospitals called Sanjeevanam Ayurveda Hospital in Kerala. And I'm also a film producer. I'm here actually in connection with a documentary film production based on this observatory, ISRO and other science and technology matters. Our director, Mr. Vinod Mangara, is also here. I'm a layman. I'm not a science-based person or anything. So one or two questions which I would like to ask you is how you identify a planet? How you identify a planet? And I still do not know what are the achievements and contribution to our country from this observatory. Because last 30 or 40 years, this observatory, you should have contributed much, but as a layman, I'm not aware of it.
Yeah, so this is the questions. Yeah. Thank you so much. Yeah, I think the questions are to me. Would you like to take it? Yeah, yeah. So the exoplanets are, yeah, thank you. Take your seat, sir. Yeah. So the exoplanets are identified using a couple of techniques. One is this Doppler shift, because when we actually see the trains coming towards us and moving away, the frequency change happens. The louds are and woo, it comes and goes, right? So that is an example of the Doppler effect. But if you can something moving back and forth, you will see this woo, woo, like this, you know, this going up back and forth. So this is a very small signal, but thanks to technology, we have developed detectors and instruments which can actually pick up these small signals. Imagine you normally say that the Earth is going around the sun. You will not say the sun is going around the Earth, right? There's a reason because that's a major movement, but there is a minor movement for the sun also. Very small movement. So this small movement can be picked up by instruments which are very less in error. So the spectrograph for this telescope, there is one out here, which is actually housed inside a laboratory. So that similar telescope, this observatory, similarly like PRL has a telescope, right now 2.5 meters is coming up, another one is also there. They also have a very stable spectrograph. So these spectrographs can actually estimate this small movements and back and forth movements in Doppler shift. That is one. Second, you can also have like eclipses. So when the small planet comes in front of the star, it will reduce the light very, very little. So 1% kind of a thing. So it's a very, very small light dimming, but again, that is precision measurements. So because of that, these two methods are helping us to estimate detect the planets. So planets did exist, but we could not detect because of the technology. So technology has helped us. Coming to second question, we have a 1 meter telescope there, which was established in 1971. 1972, Ganymede, which is one of the Jupiter's satellites, the atmosphere was discovered from here. And second, in 1977, because of occultation, we also detected the rings of Uranus. So these were the earlier discoveries. Then towards 80s, we had a unique program to detect asteroids. So asteroid detection was look at large area of the sky, Schmidt plates, and then they move faster than the star. So you can track the stars, but the asteroids will leave a streak. So several asteroids were discovered from here and named from here as well. After that, this was also built in 1980s. And then the discovery from here are mainly, this telescope is equipped with high-resolution spectrograph. Earlier, there were images and star-forming regions in galaxies, but a lot of elemental abundances and how fluorine is formed, how lithium is formed in stars, all these come from these telescopes. These are some of the discoveries. So we also have one more person, Vinod Mangara. I would like to introduce him. And Vinod, please come. So thank you so much for coming over here and being with us on the National Science Day. So your question and your message on the occasion, please.
Thank you very much. I'm very, very happy to be here because I'm very much interested in astronomy. That's why I'm here now. I'm doing this film is only because of my interest, no. And I wish to ask you a question about. No, this is based on any black hole or supernova explosion. Any that type of studies observed in this FMEA, no? Yeah, please.
So we had detected the GRBs basically means that the gamma ray bursts. So gamma ray bursts could be detected only because we had a gamma ray satellite out there. Otherwise, we wouldn't know that there was a burst by gamma ray. But then once the gamma rays was detected, we could not localize them. What is it coming from? And gamma ray normally, localization on the sky is a very large area. So how do we do it? So optical follow-up was taken up immediately. And then you immediately scan the area and see whether any brightening has happened. So this was done towards the end of 90s. And this telescope and the other telescope has contributed to follow-up studies of GRBs. Now, follow-up studies actually identified the optical counterparts. So in a galaxy, suddenly a brightening happening. At the same time, GRB was also discovered. So the long GRBs and short GRBs came into existence. And then we knew that many of them are actually associated with supernovae. So these results came towards the end of 90s and early 2000, and this telescope and 1 meter has contributed to understanding this. Now, with respect to black holes, there was a very sensational discovery of black holes and the imaging of black hole, right? So that is in the wavelength, which is not in optical, which is in the millimeter range. So you detect them, and then you map the intensity, actually. But black holes also contribute in a different way. The centers of galaxies have black holes. So like, you know, when you have interplanetary exploration, you don't know, how do you know the direction? You're totally lost with direction. So basically, quasars, which are very bright nuclei of galaxies, are taken, they're very far away sources. They are distinct framework. Even for all the satellites, those quasars are the building blocks. So even GPS works based on quasars. Your GPS on the phone or in your thing requires the satellite to position, but the satellites themselves need to position in the outer space. So quasars are actually the light beacons, which are the framework for positioning. And quasars are nothing, they have very bright black hole at their nuclei. And from this observatory, we also study the black hole accretion, that's called the active galactic nuclei, the variability. So they study from here. So any questions to sir, and any YouTube questions? Yeah.
The answer will come through this channel.
Yeah. No, there are many aspects of Aditya mission. Okay, one is what exactly is it? Aditya mission is a mission to study sun. Not to go to sun and then get like what the Parker Solar Probe does. No, it's entirely different. It goes much closer, like 5 million kilometers away it goes. Whereas the Aditya L1 mission goes to the Lagrangian point L1, which is a Lagrangian point between Earth and Sun-Moon system. So this point has a beauty that once you go there, you can create an orbit around this fictitious point. So you can stay there. Advantages, it is much away from Earth, so no influence of Earth, and you can look at Sun for a very continuous mode. That is advantage. Then, so this is the first part of it. So some rocket should take this satellite to Lagrangian point, which is almost 1.5 million kilometers away from Earth. So it is a very tough thing to go and then place it precisely in that L1 orbit. So this is called the first part of it. Then once you go there, what you want to do? You have to observe sun. And the question is, what exactly you are trying to observe from sun? Sun we are able to see here also. But once you go 1.5 kilometer away, but still there is much more distance to sun. Then the question is, what exactly you are going to see? So you need to develop instruments to look at sun. Primarily, you cannot look at the sun disk at all. You need to look at around the sun. So this is what the coronagraph is going to do. So we will hear about the coronagraph and the instrument, specific instrument. Yes.
Yeah, exactly. That is the point actually. The first challenge is the mission itself. We have never done a mission to L1, Lagrangian point. So that is one part of it. And I just want to answer, she talked about the quasars. When we talk about the Mars mission and the navigation to Mars, one of the important elements is how do you locate it actually. That location normally we do through triangulation, taking data from different points, different ground stations. Here we need to have that quasar. With respect to that quasar which is there, we relate our object. Otherwise, both will, from anywhere you look at it, is a straight line. We can't find the difference actually. So that is another thing which I wanted to add. But Aditya mission is going to be a wonderful mission, and the scientific instrument holds the next key once the satellite is put in the L1 point.
See, all of us know sun is so much important for us because it gives us energy. The sunlight is what creates the photosynthesis here, and because of that all of us are walking. That energy only we are using. But sun can also kill us within no time if there is certain physics is not around us. One of the important physics is that there is a magnetic field for Earth. And this magnetic field protects us from a big danger which is currently there. So how the flow of these particles which is emanating from sun that is trapped into the Earth magnetic field and protects ourselves, and how sometimes this may not really be able to protect, because when there are certain events which happens in sun which can create a big disturbance to our activities on Earth, which includes the electromagnetic interference with the power lines, power distribution network. It can also interfere with satellite communication systems. Recently, almost 40 satellites were destroyed, almost deorbited virtually because of the density increase in atmosphere and the drag increase. So, understanding the activities in sun and how it will influence our space weather is very important, and we want to study this aspect and make even sometimes prediction early. This can detect and then inform us before it actually arrives us. So some of these capabilities are there due to in Aditya L1.
So it's a very interesting mission, and I should also add that sun is very transient, but it also has long-term and short-term effects. So I must mention at this point that the Kodaikanal Observatory, which started taking pictures of the sun, we have the digitized version available for the last 100 years, 120 years. And that helps us to understand the long-term variation of the sun. But the short-term variations which really are the coronal mass ejections, which are coming from the coronal loops and the ejection of the mass from there. And there can have flares and, and that is to do with the sunspots, etc. So sunspot activity is a very long-term thing. But then when you have an active sun, coronal mass ejections are a primary thing which target us. So coming to Aditya L1, it has got one major payload is the coronagraph, is visible emission line coronagraph. So what corona you can see only during eclipse, because corona is very faint and the disk of the sun is very bright. So if you want to study the corona, what you have to do is you have to block that happens during the actual solar eclipse. You can see the nice patterns around it and all. That's a very dim pattern. But sun has a very hot corona. We don't know how the gas around it is so hot. So that is a question which still people are trying to address. So you need to study the corona, you have to block the light. So the coronagraph basically blocks the light of the disk. You do not see the sun. You see this around the corona. That is the visible emission line, and that what signatures of magnetic field, etc. will be there used by spectroscopic data and imaging data. Second, there's another payload which is coming from IUCAA, is the SUIT instrument, which is actually looking at the disk of the sun in ultraviolet light. So ultraviolet light tells you the upper chromosphere kind of a thing, and the connection between the lower sun, the middle sun, and the corona can be understood. And also there are many payloads on X-ray. So though you would mean that the sun is not a very hot star, which is like about 5,000 to 6,000 degree, how is it emitting X-rays? Because the emission requires much larger temperature. It's not thermal, it is coming from magnetic fields. So then the X-ray actually tells you about the corona. So Aditya L1, which is sitting there, this is basically between sun and earth, in between. So it all the time moves in front of the earth, all the time seeing the sun, and will be able to study all this simultaneously, because all the energy levels, you can study it together. So that is very important, and no time is lost because it's always seeing, and L1 is in front, so it always sees. That is very important from the scientific point of view. And it's synoptic, like you can actually chop it, and the CMEs and all the energetic phenomena can be studied at shorter time scales as well. So that is a scientific aspect of, I'm not a solar astronomer, but this is what I understand regarding the science from Aditya payload. And I also would like to ask one more question on the lunar missions, because there is a sudden interest in the lunar missions, right? Artemis, I think Artemis is trying to put people there in a few years, and I think there are some more than 10 missions planned this year itself from the US. So what do you think by the end of this decade moon will look like?
See, the interest in moon, after the first cycle of interest which was there 50 years back, it came because of the possibility of going beyond moon. It's not because there is a specific interest in moon, but if you want really to make a continuous interplanetary travel to, say, Mars, and also rescue people if you go to Mars, unless you have a station on moon where people can come back and then get rescued, it is not easy to come to Earth on a regular version, whereas it is easy to travel from moon to Mars and go back and forth. There is no re-entry involved. The risk of landing and docking are very minimal. So it all started with the idea of going beyond moon. So a space station around Earth is no longer the best idea in such a case. So we need to travel back and forth from Earth. So you use a rocket to go to a space station around moon, create a base, and then create a base on the surface of the moon. So you can establish a connection between the base on the surface of the moon and an orbiting moon station. So it allows you many things. One is, we are now talking about going beyond moon means that you need to have fuel, because all the fuel cannot be carried from Earth to moon. So you need to synthesize fuel. So one of the important technique that has come up recently is Sabatier reaction, which actually synthesizes methane from carbon dioxide and water. So from that you get both methane and oxygen. So both liquefied, you can have a rocket engine now. So you would have watched that recent rocket engines are all based on methane engines, not really kerosene engines. So the methane has become the real future fuel. So it has a potential. The moment you discover water somewhere, your ability to synthesize fuel is also there, provided there is an energy available, like solar energy. And Sabatier reaction is actually possible on surface of Earth. We are doing it already. So once you have this, you can synthesize the fuel, you can send a rocket to the moon, you can refuel station can be created on moon, and from that you can take off and go to Mars or any other planet at a later point in time. So it's a long-term plan of creating that capability. And that's the interest. Of course, there are other interests which you probably know, like helium-3, and we know that helium-3 is abundant there. So such discussions are, and also mineral extraction, which is again a very long-term technological growth requirement, because even extracting a mineral from surface of Earth itself is so tough, and you are telling so easily that I will extract mineral from moon and bring it to Earth, etc. So it may be possible at a later point in time. And we are also knowing about mineral extraction from asteroids and other objects, which is not possible to extract and bring unless you have an intermediary station. So moon as a station outside the atmosphere is mandatory for any future growth of possibility of travel. Yeah, basically because of energy. The energy required to reach moon is maybe a 90%, and from moon to Mars it is only 10%. So you can understand why that is so important.
Yeah, thanks. You have a question? Yeah, please.
What are the possibility of meteorites striking our satellites? Is there any way to avoid it?
No, all of you, maybe astrophysicists know how many meteorites are actually entering Earth's atmosphere on a daily basis. No, you know that they are in lakhs. No, not in hundreds. So that means when something is hitting Earth in lakhs on a daily basis, the possibility of them hitting any of the satellite is also very high. But the lucky part is that if you look at it in a statistical sense, that possibility is 1 in few lakhs. So it doesn't really happen. So it doesn't mean that it is not a possibility. It is always a possibility. One of the orbiting debris that hit a satellite is very much possible. Asteroid also. So let us not worry that today, but it cannot be protected. The moment that you have something traveling with 20 to 30 kilometers per second speed, I think none of us are realize that it is not possible to protect it by any other shielding mechanism. Orbital speeds are of the order of 8 to 11 kilometers per second, and any such objects coming from outer space will be having much higher velocity. So you cannot protect it. And also, you don't need huge masses to damage any satellite. See, for example, even a sand grain size object traveling at 30 kilometers per second is enough to destroy a satellite in no time. So it is very much possible, and you have no tools today to prevent it, and you have no means to even observe it. So today in ground, the maximum size minimum size that you can observe is typically 10 centimeters in size, or even smaller than that cannot be even detected by our radar equipment. So this is a risk for traveling to space. Even human beings, if you travel to space and do extra vehicular activity, the biggest risk in such an activity is being hit by an object of sand grain size flying at 30 and 40 kilometers per second. And in no time you are gone. It is a major threat. It's a major cosmic threat. Space debris, we generally call it as man-made debris, like the parts of the rocket or the parts of the satellite which dysfunctional and then or collided and generate debris. They travel at much lower speeds. But asteroid origin is much more energetic. And the question is on reusable rockets. I think reusable rocket is a story that has been there since rocket started. Because like aircraft, when you take off and then go to Delhi, you don't throw the aircraft there and you come back in another aircraft. Rocket only has this problem. So rocket falls into the sea after every mission. So human beings were realizing that reusable rockets are required, and people were trying for the last so many years. Never it happened. Even today it is not there. 100% reusable rocket is still not there. But then the partially reusable rockets are there, was what being done by SpaceX. This is the only one rocket that has come out which used to be the lower stages are reusable, whereas upper stages are still not reusable. So the real idea of reusable rocket started many years back. Many people tried. I know the names of Roton rocket. They flew 2-3 times, they fell down and failed. There was a Chrysler who worked on balloon-based landing. Again, they did one-time experiment and did not succeed. The first time anybody succeeded was Elon Musk, in terms of a commercial, conventional, expendable rocket to be recovered. Another rocket which existed for many years as a reusable rocket was Space Shuttle. But Space Shuttle was the orbital part of the vehicle was recovered, whereas the booster, the upper stages were all lost. So essentially the idea of a fully reusable rocket is still a dream. It is not yet happened. The only way to make it happen is the lower stages, after doing the mission, will come back and land the way the Elon Musk does in vertically. And upper stages is like a winged aircraft. Will go there, place a satellite, and come back autonomously and land. So this is idea we are also pursuing in ISRO. We also want to achieve that maybe a few years from now. For that, we are working on a reusable rocket, winged rocket. We call it RLV. It is ultimately meant for orbit. And the lower stages will be like what Elon Musk does. It will come back and land in with a legged, or many other means are there. Either you can land on the legs, or it can land with a balloon. We are also looking at something called aerodynamic decelerator. That when it comes to atmosphere, can you reduce the speed by drag like a parachute system? Normal parachutes will not work. We call it IAD. We are going to test it soon with a sounding rocket to demonstrate the technology. And we would like to do it slightly differently from Elon Musk in the future.
A few things ISRO has already done. One, of course, when you have a early stage finishing its job, it comes very close to our coastline. How do we recover it safely? There is a problem once upon a time for us, whether PSLVs stages can be brought back was being asked. But if you look at the space recovery experiment, we were able to bring from orbit and get into a place very precisely and also bring it back safely. Same thing we also did in the CARE module in 2014. That module from the atmospheric re-entry was brought back. So one such thing has been done. They had somewhere in 2016 the reusable launch vehicle technology demonstrator. It also studied a combination of a rocket and an aircraft. All the issues that both of them will encounter during the ascent phase and the descent phase were tried out. As a technology experiment, that was a successful thing. The third thing which was not mentioned is how to use the oxygen in the atmosphere for the propellant. This is something which is a wonderful experiment. A lot of things are happening.
Yeah, that is called air breathing engine. We had done a test during 2018, an experiment which was successful. It basically uses the air in the atmosphere. Fuel alone we carry, and combustion takes place and generate thrust. And we want to do it again. We are having another experiment coming up called the HAWA, hypersonic air vehicle with air breathing, where we can travel almost 1,000 kilometers in just 20 seconds. So very high speed hypersonic flight where this air will be compressed internally and combusted. So this technology is also available. Possibly, we are not telling it will be used in rocket immediately, but we are developing this technology for future reusable rockets.
So that was a very interesting question, and so much about the future going to be, and I think it's very lot of technologies, lot of ideas, lot of aims to move forward. So amazing. It was very nice insight from both of you. Thank you so much. I just wanted to ask you just any message for the National Science Day from any particular message you have for upcoming people. There will be a lot of
from the Space Agency of India in ISRO, since I am here, and there is an important announcement by government in recent days that is called space sector reforms. It is to bring you young people, new entrepreneurs and new actors into the space sector. So this is not for building rockets, satellites, applications, but also new science. Those who are very passionate about all of this are now enabled by the government. With the support of ISRO, you can build, launch and operate space systems in this country. And so this is a big change that has come. So it only tells us that in the non-governmental sector, all these can exist. Somebody wants to build a rocket, it is going to be possible. Somebody wants to build a satellite in India, outside ISRO, it is going to be possible. And you can also launch them using your own rocket from your own launch pad. Okay, so that means ISRO is not going to stop the work. We are going to help all of these people to build it. And so that in India, such capabilities are expanded big way. So this is the direction that government has given us, and we are preparing ourselves to take on this challenge through creating appropriate legal framework, operational guidelines and institutions to enable this to happen. So this is something wonderful. Slowly, I believe India will become one of the leading spacefaring nation. Maybe to have as Dr. Radhakrishnan sometime mentioned, $400 million US economy, it will grow to something like 1.5 trillion economy in the coming days. Our share today is only 1% to 2%. We wanted to increase to something like 10%, at least in the near term. So this is a goal. I believe it will really happen.
Yeah, okay, that's I mean, takes the entire amrit of the message to the upcoming generation, and it's looking really, really positive. And we look forward to this decade with all these missions coming up, as well as technology opening up to private sectors. A lot of entrepreneurs and startups going in forward for us. And thank you so much for all your words, kind words and directions to all the audience out there as well. Thank you so much for joining, and thank you people on the floor. And we had a very nice session here. Thank you so much all. Yeah.